In this video, we're going to explore the method that is known as the disk method. Right? This section talks about the disk and washer method. I'll post another video that goes through exactly what's going on with the washer method. I didn't want this one to get too long. So what I want you to do is kind of imagine you've got some general function, say f of x, between two values a and b, right? We know how to find the area under this curve between a and b, right? That's a simple integral as long as our function is positive, right? Now what I want to do is take this region, shaded in pink there, and rotate it about the x-axis. And what we get from that is going to be a three-dimensional solid. So I take that chunk of area and I'm going to spin it around the x-axis and I'm going to get some solid that looks about like this. Okay? And that solid is going to have a solid volume. I'm going to want to find that volume. And that's what this section's all about. In the next two sections, actually, is finding a volume of what we call a solid of revolution. So again, we take the area under f of x, we rotate it, and what we obtain is a solid of revolution. Okay? And there's specific ways we do that, and there's specific techniques we want to do. The x-axis here would be called our axis of rotation, or axis of revolution. Okay? So that's going to be a specific bit of information that we need to know as we go to find the volume of such a solid. Okay? And the way we're going to do this is very similar to how we looked at area before. I took a chunk or a slice of my region that I used to represent the entire piece of the area, right? So I called that my representative element of area. I'm going to do very much the same thing with a solid of revolution. I'm going to take that slice and I'm going to rotate that slice around. And when I do that, I'm going to get a disk. Okay, so that slice rotated around the x-axis by itself is going to give me a portion of the entire solid, and that disk is going to represent the volume of the solid, and I'll be able to find the volume of that disk and then hopefully integrate. Okay, so there's the same picture I just drew, and what I want to do here is show you what it looks like when I rotate that disk about the x-axis. Or rotate that strip. I get a disk just like that. I've colored it in for you. Okay? So, what I want to do is describe the dimensions of this now disk, right? It's three-dimensional. And I know its radius is exactly just the height of the function, f of x, right? I took the height of that function in the slice, and I've rotated it around the x-axis. I've created a perfect disk, so the radius of that disk is the function. I've also got some thickness there, and that's just going to be our dx. What I want to do is I want to rotate this picture on its side, because I think it helps us describe the disk itself. So I've just rotated that picture for us. I see the radius there. And that thickness, we often describe as like the kind of the height. When it's vertical, it's kind of hard to describe as height, but you can think about it like some height or some thickness. Okay, the volume of this disk is what we call dV, and it's going to be the area of kind of that top surface times the height. Right, the area of the top surface is pi r squared times the height is kind of our general formula for a volume. It's basically like a cylinder. That's what we're kind of working with, right? Or I'm approximating it with a cylinder. We know what r is. We know what the radius is. That's the function f of x. We're going to square it, and we know what the height is. It's just the thickness of our slice. It's dx. Okay? That dV is what we're going to use to represent the entire area, the entire volume of the solid we get when we rotate the entire region about, say, the x-axis. Okay, and just like we did with area, we took our representative element of area, dA, and we integrated it. So we're going to do pretty much the exact same thing. I want to show you what the entire shape looks like and how that slice kind of comes into play. So this entire shaded region is what's being rotated about the x-axis. Again, that area is exactly the integral from a to b of f of x dx, as long as f is positive on a to b. Okay? So now I rotate it, or revolve it, I use those words interchangeably, about the x-axis. Okay, the entire region. Again, I get this new shape, and it's going to be a solid of revolution. And I want you to think about inside that shape, I take the slice, shaded in pink on the left, and I'm going to redraw it as the disk from the previous page. All right, I've got this solid, and inside there's a portion that's that disk. I look at the dimensions of that disk there. I'm just going to outline it for us a little bit. Again, it's pi times the radius squared times the thickness, and that's pi f of x squared dx. And what I want to do is integrate this guy to find the entire volume of that solid. Okay, so what that looks like is pi, the integral from a to b of f of x squared dx. And that's going to be our general formula for the disk method. Okay, that's our general formula as long as we are going around the x-axis. Okay, so that's important. I need you to be able to kind of adjust if we're rotating around some other axis. Okay, but in general, that's what the formula looks like. I'm going to try to use that to go through another example here, and then I want to change things a little bit and work on something a little bit more complicated involving this disk method. Okay, so here's my first example. Find the volume of the solid formed by rotating the region bounded by the function y equals square root of x minus 1, x equals 1, x equals 2, and the x-axis about the x-axis. So about the x-axis tells me where I'm rotating this region, okay? And what I've got colored in pink, purple, and blue there is going to give me the basic outline of my region, okay? I'm also going to need the x-axis to finally close in the region. I want to draw a picture here. But there's our formula for our disk method. I'm assuming that's probably what we'll use. We should be careful. So let's draw this guy here. I've got the xy axis here. And there's the start of my function. Okay, so what I'm doing here is I try to figure out how I graph this guy. When x is 1, y is 0. So I know when x is 1, I'm on the x-axis. When x is 2, y is 1. So that's where that extra point comes in. 1 and 2 happen to be my A and B, right? Those are what are blocking my region in to the left and to the right. Also bounded by the x-axis, that's from below in that yellow mustard colored line there. So again, I'm using kind of the square root of x to describe how this function behaves. It's just shifted to the right 1 unit, okay? So I want to take that region I've shaded in yellow and rotate it now about the x-axis. I want to show you kind of what that looks like. So when I do that, I'm going to rotate this rotate this slice around the x-axis, and it's going to give me a disk. So what I see here, when I rotate this guy, it's got specific dimensions here, dx, width or thickness, and a height of the function, right? Whatever the height of that slice is made by the function, okay? So when that slice is rotated about the x-axis, it becomes a disk. And we can sketch that. I rotate my region around and I get this kind of shape here, and I see that disk kind of in between, all right, or somewhere along the way. So this kind of looks like a cone, but with some curved sides. It's not necessarily perfect, but inside I see that slice. Okay, so what I want to try to do is set up the volume of that slice and then integrate it to get me the volume of the whole thing. So this area of the slice is pi times, is pi times the radius squared Again, the radius of that slice should be the function. Square root of x minus 1, I'm going to square that and multiply then by the thickness dx. When I go to integrate, I'm going to simplify a little bit. I can bring the pi, that's a constant, out front. Integrate, I'm integrating from 1 to 2 because that's the leftmost x and the rightmost x where my region is bounded, right? When I square the square root of x minus 1, I get an x minus 1 by itself, dx. Okay? The integral here is really straightforward. I want to make sure that you kind of understand where all those parts come from, because that's really the new stuff here. That's really, forming that disk and deciding what the volume of it is so that we can integrate. Describing your picture so that you can get the disk, get the volume is really the crucial stuff here. Integrate, I get pi times x squared over 2 minus x, evaluated from 2 to 1, and I get something like pi over 2 as the entire volume of that solid of revolution. Okay, cool. I want to do another example here where the region that we take around is maybe described a little differently, something a little bit more challenging. Find the volume formed by revolving the region bounded by y equals 2 minus x squared and y equals 1 about the line y equals 1. So what I want to do is try to, again, sketch a graph of this function here and the region itself that I'm revolving and how that's described then as a disk, or how that pertains to the disk method. Okay, so there's my coordinate axes. 2 minus x squared, when I try to graph, that's a quadratic, it's a parabola, and since there's a minus in front of the x squared, it's opening downwards with a y-intercept of 2. Okay, so I've got this parabola opening downwards, starting kind of with a vertex at 0, 2. There's my 2 minus x squared. I could find the x-intercepts to kind of help me out and make my graph, a little bit more clear. I don't really need them in this case. I'll show you why. I also need to graph y equals 1, and that's the horizontal line with a height of 1. Okay, so the region I'm working with is bounded by those two functions. It's everything in yellow here. And I want you to notice that that region is above the x-axis, right? I've got some missing space, okay? So what happens, and now when I rotate this about the line y equals 1, I've got to be a little bit careful. The regular formula I know for disk method isn't exactly going to work here because, again, that only worked when I was rotating about the x-axis. I've got to be careful. So I draw my slice. Here inside my region, okay? And that slice, I'm going to be revolving about the line y equals 1. When I revolve that slice, I'm still going to get a disk, okay? I'm not revolving around the x-axis. I'm revolving around the line y equals 1, okay? That slice has a thickness dx and a height that's a little bit tricky to find, okay? The height of my function is the height from the x-axis to my curve, right? Not just the height of that disk or that slice, but the height of the function goes up to the function from the x-axis. The height of the line y equals 1 is 1. It's 1 unit up, right? What I'm looking for is actually the remainder that I get from subtracting those two. The height of my slice is f of x minus 1, or 2 minus x squared minus 1. So this is tricky. This is why this example is a bit more difficult than the last. I can't just say, oh, the radius is my function. Done. Not quite, right? If I were to draw that disk, I would see that the radius isn't just the height of the function, but it's height of the function minus that gap that I'm leaving kind of in between, okay? If you want to draw the actual disk or draw the entire region, that solid of revolution, you absolutely can. What I want you to try to remember, we look at this very much the same way as we looked at area, right? If I was trying to find the area of that region, you would do top curve minus the bottom curve, right? In your integral. The height of the or the radius of the disk is exactly the same, right? It's the top curve minus the bottom curve. 2 minus x squared minus 1. Okay? So the area or the volume of that slice then, when I rotate it about the y equals 1 line, I get pi times the height, the radius, 2 minus x squared minus 1, all squared, times the thickness dx. Okay? I'm going to simplify as I go here. I'm ready to write down the volume. Is the integral, I need to find the bounds. Those weren't given to me, right? Kind of like they were last time. This time, the bounds are going to be where these two functions intersect. So I set up the equation 2 minus x equals 1, and I solve, and I obtain that these two curves intersect at plus 1 and minus 1. So the bounds of my integral will be plus 1 and minus 1. Okay? So I'm ready to integrate from minus 1 to 1 of 2 minus x squared minus 1. When I subtract 1 from 2, I get 1 minus x squared. I'll write that in a second. I want you to also notice that the region I'm working with here is symmetric, right? It's symmetric about the y-axis. So I can actually kind of split things up and integrate not from minus 1 to 1, but from 0 to 1 and double it. All right? That's not necessarily required, but if symmetry is available, it usually makes the integration easier. And I'm integrating 1 minus 2x squared minus x to the 4th dx. So I've already taken 1 minus x squared on the inside, and I've squared it to get 1 minus 2x squared minus x to the 4th. And again, the 2 on the outside came from using the symmetry about the y-axis. So I'm integrating from 0 to 1 now. It makes my integration just a little bit easier when I use my fundamental theorem of calculus, right? When I evaluate the antiderivative at 0. And I'll quickly do that here. Integrating, I get 2 pi times x minus 2x cubed over 3 minus x to the 5th over 5 from 0 to 1, and I get 16 pi over 15 as the total volume of the solid created by revolving that region in yellow there about the line y equals 1. Okay, so this is another application of disk method, but some of the key takeaways here are that what's on the inside of my integral wasn't just the original function, right? I had to consider the height of the disk that I was working with, or the height of the region there, in order to get the appropriate volume of the disk and then the appropriate volume of the entire solid. Okay? In the next video, what I'll do is I'll outline how we use what we call the washer method. And actually, as a precursor to that, I want you to think about what would happen if I take this same region, not change the region at all, and rotate it about the x-axis instead. If I do that, I've got this entire blank space here that I need to pay attention to. And we need to find a way to kind of remove that space from our solid. Okay? But for now, this is the disk method. Practice some different examples. Thank you for watching.